Doesn't show any. Okay, perfect. Our first speaker is going to be Francesco Salvatore from CNR. Then we will have one of the long sessions with David Davignon from EMEC on the in situ observations for WAVE. After his session, we will have a short Q&A. Then we'll have a very brief break, and we will continue with in situ observations for Tidal, and a final recap and finalize with Francesco and Mohamed from CNR. If you have any issues, any technical issues, please use the chat function, and we'll get in touch with you and try to figure out how to solve them. Regarding the questions for the speakers, please use the Q&A function. Thank you. And I think the program has been shared already in the chat, so you can click on it. That's the final program. We will also be uploading both the presentations and the recordings into the project's website as when we finish the whole course. And in case you haven't done it yet, you can also sign in to the second session on September 3rd. Welcome all. And David, are you ready?
I am ready, yes.
Okay. So David Davignon is the Senior Metocean Engineer. He oversees EMEC's metocean data collection, quality control, criteria development, and provides support to various stakeholders with regards to metocean information. Welcome, David.
Thank you. Thank you very much. Was Francesco going to say a couple of words first?
Oh, yes. I'm really sorry. Francesco is first going to introduce monitoring and resource assessment. I'm sorry.
Thank you.
Welcome, Francesco.
Okay, so good afternoon, everybody. Thank you, Marina, for the introduction. I'm going to share my screen. Hopefully.
Okay. If you need any support from my side, yeah, we can see your screen.
Okay, perfect. So again, good afternoon, maybe good morning, everybody. I don't know, since this is a webinar, of course, with potentially global extension. So we are very happy that we can share our experience inside this project funded by the European Commission with a so wide community of interested people. So this is just to introduce the topic of the two talks that we are going to have today about monitoring and resource assessment for two areas. One is wave energy and the other one is tidal energy. And this is the summary of this first introduction. Of course, we will try to put the renewable energy technologies inside the present challenges about the net zero targets. We will try to picture the status, the state of art of marine renewable energy technology. Just a very quick introduction, if necessary, to the technology readiness level scale concept, and the contribution of our project, the MaRINET2 project, in the area of the development of this technology. And finally, we will introduce, of course, the real subject of these webinars. On the right of your screen, you can see two pictures that describe the environments that we will virtually visit today. And we can see two extremes. Just to imagine, we are in the areas where the speakers are coming from, in particular the Orkney Islands, where David works for the EMEC Center. Which is a place famous, of course, for marine renewable energy resources. But below we can see a more friendly, let's say, scenario, which recalls maybe more the concept of summer holidays rather than energy. And this is a small island in the south of Italy, where there are also ongoing plans for the exploitation of wave energy. Well, so we can start. Of course, never, as in this period, it is timely to talk about renewable energy, and it is already well recognized that renewables from marine sources, like in particular waves and currents, are particularly important because this is a nearly unlimited but actually still untapped resource. And this can provide a great contribution to the renewables energy mix, which is extremely important when renewables and to some extent unpredictable resources are being considered. And since this is a new technology, this is expected to represent a real boost for economic recovery and sustainable development. Everybody knows that global or regional organizations are setting continuously changing climate targets. For instance, in Europe, at the moment, we have some challenging targets for 2030, which means reduce 55% the emissions with respect to 1990. Only a few years ago, this target was only 40%. And to reach net zero by 2050. So, dealing with marine renewables, this is a growing technology with a growing supply chain, but with a number of interesting megawatt scale projects that are already deployed or under consenting. Of course, this technology is growing, but already competitive in niche markets, as in the case of small islands and remote communities in coastal regions. And we are already in front of measurable targets that have been considered, for instance, at EU level, about 3 gigawatt installed by 2030 and 100 gigawatt by 2050. So, a new technology with a lot of challenges, of course. First, demonstrated economic viability and environmental sustainability of commercial scale projects. This means to increase efficiency and reliability, higher power output, capacity factor, easier and faster installation, retrieval for maintenance, and decommissioning at end of life cycle. Smart maintenance is also a new ambition, means predictive or remote maintenance, and standardization. Standardization in particular is expected to provide a reduction of costs. In particular, the levelized cost of energy targets for 2030 provide 90 euro per megawatt hour for Tidal, and a little bit more for wave. This difference highlights that there is a general perception that tidal energy at the moment is a bit closer to technology readiness than wave is. And this is something that brings the concept of technology readiness level that maybe most of you will have familiar as a concept. Basically is a standard way to measure the technology maturity of a process or a product. This has been introduced by NASA for the aerospace sector, but has been widely adopted also to classify offshore renewable energy technologies. Of course, from this very general concept, in the past years, some organizations working in the marine sector have developed their own declination, let's say, of the theoretical concept more suited for marine renewables. And for instance, the International Energy Agency, and in particular the Ocean Energy Systems Department, developed some guideline in order to establish what is the definition of a technology development stage, what are the relevant testing infrastructures where this technology is being considered at some given TRL, what should be the purpose of testing, and what should be the characteristics of the model scale and subcomponents to be involved in testing. And this brings to testing, which means developing, assessing, validating, demonstrating a technology. And in the project is bringing a great contribution for the maturation of the offshore renewable energy sector, in particular with integration and enhancement of leading European research infrastructures, specializing in research, development, and testing of marine renewable systems through a range of TRL between 1 and 7. Here you can see some figures about this project. The project considers 4 areas of expertise articulated in 6 technical work packages. We have a standardization of testing facilities, digital infrastructures, and 2 work packages that are closely related, for instance, with the course today, training and communication, and another work package which the activity which represents the focus of the project, which means the transnational access. In practice, free access for testing to infrastructures where the budget is financed by the European Commission because of the project. So, in order to provide this service to the community, the MaRINET2 project has developed a research infrastructure community with 57 testing facilities across Europe, including 3 virtual, that can be grouped according to the type of energy of technology that is being harvested: tidal, wave, offshore wind, or grid connection or electrical systems, and cross-cutting activities like materials and moorings. Then we can also group these facilities according to the dimension of the laboratory or field site testing facility, and correspondingly the TRL of the device that are worth to be tested in this area. Relevant for the talk of today, we can concentrate on the TRL of 5 and higher, because between 4 and 5 there is a major milestone, which means moving from testing at a laboratory scale, a simple device, typically a small device, to deploying something bigger, something more complete in terms of subcomponents into real waters. And this is, of course, the subject of today. Here you can see a list of devices for wave and tidal energy, and for instance, these are 2 different testing sites relevant for tidal energy devices. One is for the first testing in real tidal site conditions, which means what we call Benin scale conditions, where the current is not that high, the wave climate is relatively mild, and you can come with a near scale device which is not fully completed in all its parts. But when your technology is ready, you can deploy a full-scale device in a more challenging environment. And for instance, EMEC in the Orkney provides a number of berth points in order to deploy a full-scale device and connect to the grid, which is, of course, very important in order to achieve the full characterization of this. So, field test sites. This brings to the subject of today's talks, which is in situ monitoring. Basically, we have 2 main objectives. One is to characterize environmental factors affecting device operation over a range of spatial and temporal scales that are relevant to the designers and operators. And related to this, investigate and assess the impacts that these devices can determine on the environment, both locally at site scale or at a wider scale. This is being performed through a multidisciplinary and complementary number of activities. Basically, we can group into field site metocean conditions, resource assessment, device performance and operation, and environmental impact. And the focus in today's talk is about resource and device. So this brings back to the agenda that Carolina and Marina have already presented. So the next talk is with David from EMEC, who will guide us in the world of in situ observations for wave energy systems. Thank you very much for the moment.
Thank you, Francesco. We'll see you later again.
Yeah, thank you.
Okay, shall I go on then?
Yes, please.
Yeah, thank you. Yeah, I think the introduction was already done, so I should be okay. Let me see. There we are. Is that the presentation itself? Is this the slides, right? Not the presenter mode, hopefully.
Yeah, we can't see it yet.
Oh, perfect. Okay.
No, sorry. We can't
cannot see
the
your presentation yet.
Oh, it didn't come up yet. Sorry.
No.
Yeah. Okay. Let me see. Should come up now, probably.
Now it's.
Yes, can you put it in presentation mode?
Yes, I was.
Perfect.
Yep.
Thank you.
I was just rushing a bit too much. Okay, got there. Thank you very much. Thank you, Francesca, for the introduction and for passing it on to me. So I will talk about in situ observations and waves. My name is David Darby, and I work at EMAC, and I'm a network engineer there. So I put up a content of the talk. I tried to cater to as wide of an audience as I can. So for those of you who are working with waves quite a lot, it might be a little bit. There might be quite a few basic things, but hopefully when it comes to marine energy, maybe some interesting things will still pop up. But I'll talk a little bit about. We'll have an introduction about EMAC and why we collect wave data and where do we live. Then we'll move on to basics of ocean waves, a little bit of theory which is relevant to in situ observations. Then we'll move on to in situ observations themselves, what instruments we can use and where we use it and what we do specifically at EMAC. Then we'll cover two very important pieces, two very important steps, which is quality assurance and quality control of the data collected. And then we'll go into a couple of slides about good practices for data handling, which is quite important for us as well. And I'll cover in a second. So EMEC, as Francesca said, yes, European Marine Energy Centre is located in Orkney Islands to the north, at the north of Scotland. We have two sites: a full-scale tidal test site in full awareness and full-scale wave test site in Billy-Crew. The wave site is located on the western coast of Orkney, which is a great place for that type of work for testing the wave energy converters. Because essentially, if you stand at the west coast of Orkney and look to west, next big landmass you would see will be Canada. And since all the water masses are moving from west to east in that area, you've got pretty much unlimited fetch for creating huge, very energetic seas for waves to be crashing into Orkney. So pretty good place to test the energy production, but also the survivability of devices. EMEC been around for more than 15 years now, close to 20 actually. And all that time we've been collecting wave data. At first we're collecting at different short periods, but then we start collecting them continuously. So over 40 years of cumulative wave observations, which means if we have 2 or 3 Waveriders deployed simultaneously, which we had in quite a few occasions, we will sort of add it all up together and gets over 40 years. One important and relevant thing, which will probably pop up through the whole conversation, is that EMAC is accredited test laboratory. So we're accredited to ISO 17025 standard as a test lab, as the same standard that applies to medical labs and so on and so on. And because of that, quite a few things which are generally good practice are mandatory for us. We have to implement some things related to data collection and data processing, and they have to be in place. So moving on, how do we use data at EMAC? We use it in sort of standard metocean ways quite often. That is, using it as a ground truth data for model calibration and verification. That's one usage. Because we have such a long data set, over 10 years, we do use it directly inside characterization as well. It is a little bit short on the short side for extreme value analysis, but still could give a good indication of the conditions. But we use it to calculate extremes, operational statistics, and something very specific to marine energy is the resource, where the sea where we operate is not just the environment, it's also the resource itself. And our accreditation comes into play when we do power performance assessments. So we measure the resource, the waves, and then measure the electricity produced by a given wave energy converter and calculate that converter's efficiency. So that's essentially power performance assessment. That type of work we do under accreditation, and that's where we have to meet a fairly high standard to how we deal with the data. Now I'm going to move on to a little bit of the basics, just that we are on the same page with all the terminology, and maybe a short reminder for what we're talking about. So the simplest wave is a simple linear sine wave where you have crests and troughs following one another. Wave height in this case is the distance between trough and the crest, and the height between crest and trough, and the wavelength is distance between 2 neighboring crests. Wave period is the time that passes between the passage of 2 subsequent crests. And the frequency is the inverse of the period, right? So if you've got a wave period, the frequency is 1 divided by wave period. Just a reminder, I know most of you know all that stuff, but it becomes relevant when we talk about the processing of the data. The waves I will talk about are just one type of the waves that you will see in the ocean. Ocean being very thin and layer on the surface of the Earth. Experienced a lot of forces on it, and they manifest themselves as periodic phenomena on different scales. The ones I'll be talking about, and the ones which are wave energy converters utilizing, are the ordinary gravity waves. That's a great diagram developed by Walter Monk at the middle of the century, and shows all those phenomena in the scale of its relative to its wave period. So the ones we are talking about are ordinary gravity waves with typical periods from 1 to 30 seconds. Then you've got a lot more high frequency stuff, including capillary waves and so on, and a lot lower frequency things like, say, tidal waves, and that's something that Francesco will cover later. Maybe another one to point out here are infragravity waves between 30 seconds and 5 minutes. They are not really relevant to marine energy, but are relevant to some types of instrumentation. So I'll probably mention them once more on the way, slightly later in the slides. Okay, we'll move on to wave energy. Again, just a reminder that a wave, ocean waves, a passage of ocean waves, there is no transfer of matter, right? So water doesn't flow anywhere. It's a transfer of energy. And that's achieved by circular, in theory, circular motion of the particles, of the water particles with the waves. So the path is, in theory, is closed. So they don't go anywhere. They just move in the same location, but are passing the energy. And that's the energy which is, which the wave energy converters are harvesting, trying to harvest. There are different technologies, different partake of methods. There are a few nice animations here with the point absorbers and attenuators and so on. A rotating mass, which is essentially what you have in mechanical watch, which is within a lot bigger size scale. I said in theory the wave orbital motions are circular because in reality they aren't. If there is an influence of the seabed, they become elliptical, and in addition, they're not closed. They do. There is a small transfer of matter as well involved called Stokes drift. So realistic wave conditions, all that we're looking at were simple sine linear waves looking really nice and tidy. But realistic wave conditions are very different. That's partially because big long waves created by strong storms have a tendency to preserve energy really well. So if the waves are created in one location with a strong storm, by a strong storm, they propagate to long distances and can be experienced somewhere far away. So in any given location, you might have your local waves created by local winds, and also different swell coming from different directions, having different periods, and it all gets summed up into a fairly complex, sea surface, changing sea surface. So the sea surface elevation you could see here is just in 2 minutes. I think it's measured at the EMEC, fairly benign conditions actually, but you can see how complex it is. It's really hard to work out what exactly we're looking at. It's not a nice linear wave with troughs and crests. To make sense out of it, and this whole theory, whatever reminder theory I'm putting out here, will come up when we talk about the way we process the data and collect the data and so on. So not just putting it here, it will be useful down the line. So to deal with that complex surface elevation picture that we get, we use spectral analysis. The idea behind it is if you take any fairly complicated signal, you can deconstruct it into a sum of simple sine functions. Once you get that, you could describe your complicated signal in terms of spectra, which means you would look at the energy which is contained in the frequency bands. So essentially, you look at the amplitude of those individual sine signals. And knowing their frequency, you can draw a spectra that shows you the energy against frequency. So what it does essentially, it switches from time domain to frequency domain. To do that, we use fast Fourier transformation. Well, commonly, the most common way is to use fast Fourier transformation. And one of the things about the fast Fourier transformation is that it requires number of data points 2 in the power of n, and that will again pop up a bit later when we talk about the way we process the data that we collect. Once we get a spectral data, we could then, it is still fairly complicated way to describe a sea state. So you've got the frequencies, you've got the energy against the frequencies, and it's a bit difficult to put just one number to it. And that's where the spectral parameters come to play. It's succinct and informative way to describe the sea states. Some of them are listed here. There are loads more. I can't remember from the top of my head, but I think when we do analysis of our data, we would produce roughly close to 40, 50 different parameters. Some examples here are peak period. That's the inverse of the frequency of the highest value in the spectral density. So I put here an example with two spectral peaks, one at 2.5 second, one at 5.4 second, or you could see the frequencies there as well. In this particular case, the higher peak is the one at 5.4 seconds. So you would say that the peak period for this particular sea state is 5.4 seconds. And then most of the rest parameters are calculated based on spectral moments. So I put here the formula for spectral moment n. So 0th moment is m0, and that 0 propagates under the integral and is the power of the frequency will be 0 in that particular case. So significant wave height is calculated from the 0th moment. And then energy period is relationship between different moments as well. I put just one formula. I thought I personally struggle reading formulas of slides and presentations. So I thought I'll probably try to limit to one. Everything else could be found in literature. In addition to spectral parameters, having collected the raw high frequency elevation of the sea surface, we could calculate some parameters which are based on time series. It could be maximum individual wave height, which is the difference between the neighboring, the maximum difference between neighboring troughs and crests, then the average zero crossing period, and so on and so on. They are very useful as well, and they're good, especially if you can use them in combination with spectral parameters, especially if it comes to quality control. And I'll probably mention that as well down the line. So that's wave parameters. And now I'll probably move on to the in situ observations overview. Will be generic overview of the ways we measure waves. But I will go into more detail with surface buoys and especially how exactly we use them at EMAC and what might be the things that we have to look into here. So we're talking about in situ observations, which are as opposed to remote observations, remote being satellite observations, HF, X-band radar, although I'm going to mention a very specific type of measuring waves using a downward looking radar in a minute. I've put 4, which I think are probably the most popular ones, the most commonly used ways of measuring waves: downward looking radar, surface buoys, acoustic Doppler current profilers, pressure sensors, and downward looking radar. I'll go through those in a reversed order though, because I'm going to leave the surface buoy to the last. We use it most at EMAC, and all the quality control and quality assurance examples I'll provide will be based on the surface buoys. So we'll probably start over with the vertical radar then. Actually, maybe one other comment about the direct in situ observations. From the previous slides, it's probably now clear that to get the spectral parameters or just any good description of the sea states, what you need to measure is a displacement, the change in the sea surface elevation at fairly high frequency. So you would want to measure it at least a few times in a second, at least twice a second, maybe once a second at 1 hertz is the probably lowest you can go to get meaningful values. Because of that, majority of the methods are based on measuring the surface elevation, majority of the in situ observational methods. And from that, you could calculate the spectra and then spectral parameters and so on and so on. So vertical radar is a radar which sends electromagnetic signal It's normally pointing downwards to the sea surface, and it's sending electromagnetic signal with a very high frequency, 10 times a second, 10 hertz. Based on a time of travel between the radar and the sea surface, you can calculate the distance from the radar to the sea surface. As those radars are normally fixed on a structure, so they don't go anywhere, it's only the sea surface that changes. So using that distance between the radar and sea surface, you could get the sea surface elevation, change in sea surface elevation, and then do all the analysis, calculate all the parameters. A couple of limitations of the methodology. First of all, you need a structure, which isn't always available. These are very popular on platforms, on substations, offshore substations, and so on. Less so in some greenfield development conditions, just because structures aren't there. A single radar can be used for only non-directional, and to get directional signal, you would use several radars, looking at slightly built setup. Pressure-based measurements are getting less and less popular, I think, but they have their own, they have a use. I've seen quite a few instruments being discontinued these days. The idea behind it is fairly simple as well. As the waves pass, the height of the water column changes, so you will have the water column under the crest will be taller than under the trough, and the height of the water column is equal to the mass of the water, which essentially is the pressure at the, say, seabed. So the mass of the water is equal to the pressure on the seabed. What you could do, you could then put a high resolution, high frequency pressure sensor at the seabed and start measuring the change in the pressure, from which you can reconstruct the sea surface elevation. There is a quite serious limitation to that method, though, because the pressure is measured only at the level of the sensor itself, and the waves, the energy, the wave signal, the detectable waves attenuate quite quickly with depth. So deeper you go, less small waves you can detect. So deeper you go, higher is your cutoff period, below which one you won't see any waves. So if the pressure sensor goes at the depths of, say, between 40 or 60 meters, waves below, say, 9-10 seconds will not be detected, which means pretty much the whole local wind generated part of the spectrum won't be seen. That's a pretty serious limitation, although there are some uses of the pressure sensor method as well. And I think I'll mention it in the QA session as well, in a couple of slides down. Quite popular way these days of measuring waves is using acoustic Doppler current profilers. Forgot the word current there, but that's the instrument which is used to measure ocean currents, and probably Francesco and Mohammed going through the presentation next would mention those, for instance, the observation of tides. So I'll only cover very briefly. The idea is that the ADCP sends an acoustic signal, and based on the Doppler shift of the reflected signal, we can calculate the current speed. When it comes to the waves, there are three ways ADCPs can be used to measure waves. One is based on pressure, because most of them, if not all, come with a quite accurate pressure sensors, but that comes with the limitations that I mentioned earlier. The other way is using surface tracking, because the acoustic signal, you can detect really well the surface from the acoustic signal. There's a spike in the strength of the reflection. Older generation ADCPs used slant beams, which means the surface was a little bit harder to detect. But newer generation ones have a vertical beam looking straight up, and the principle of operation of that one is pretty much the same as the radar we discussed. just using acoustic signal in this particular case. So it's essentially an inverse altimeter. And the third method with ADCPs is using the orbital velocities, the ones that we mentioned when we were talking about the energies that the water particles move in a closed pattern. If you measure currents fast enough with a high rate, you could extract that signal out of the current measurements and do the analysis. Surface tracking and pressure sensor are non-directional and with pressure sensor limitations, of course. To get directional data, you would need to use the orbital velocities and measured from slant beams as well. And the problem in that case is that the acoustic footprint of the beams, those beams, they separate, they diverge quite a lot deeper you go, right? Because they're at the angle. So if your ADCP is deployed quite deep, the distance between the two beams will be quite wide at the surface. And to do the directional analysis, you need the data from all the beams. So the smallest wave that the ADCP could detect had to fit into that acoustic footprint at the surface. So any smaller wave than the distance between the footprint won't be detected by the ADCP. So now the last of the list, but not from my list, but probably the most commonly used one, almost sometimes referred to as a gold standard of wave measurements, is a surface following buoy. It's a floating body, and it's designed in such a way that it could best react to pretty much any waves as small as possible on the sea surface. So it sits on a sea surface and bobs around. The idea is that that moving buoy on a surface would measure displacement in three directions, in three components of displacement: up and down, essentially the surface elevation, and then north, south, and east, west for directional calculations. It can be achieved in several ways. Two popular ones is 3-axis accelerometer on the buoy, used to calculate the displacement, or GPS-based, which are becoming more and more popular these days. They are a lot cheaper. The surface buoys are very sensitive to the moorings. It's important to pick up the right mooring to make sure that it can follow. They can be on the surface. Follow the surface freely. It's not restricted in any way, and also very sensitive to the currents where they're deployed. One of the big advantages of having real-time, of having the surface buoys, is that you can get the data out of them real-time because they're on the surface. They can transmit. They have got an antenna. The instruments that we use at EMAC, the wave buoys that we use at EMEC, are all based on 3-axis accelerometer. And the reason for that is, as an accredited lab, we have to have our equipment calibrated where possible. And not all oceanographic equipment can be calibrated. So GPS-based buoys don't get calibrated, while the accelerometer-based buoys can be calibrated. And that's the reason that we have to use those buoys. So the ones we use are Waverider Mark IV. We've got started getting Mark IVs as well, but the principle is pretty much the same. It's just Mark IV is collecting data at higher frequency. So I thought I'll put here an example of what we get out of Waverider Mark III and what we do with the data afterwards. So as I mentioned, the buoy collects a displacement in 3 axes, up and down, north and east, north, south, east, west. The sampling is at 1.28 hertz. So we sample at slightly less than 1 second, every 0.7 something second. can do the math in my head, 1 divided by 128. That results in 2,304 samples per 30 minutes. And 30 minutes, that's sort of the standard chunk you take from the Waverider to get to calculate all the spectra and spectral parameters. Could probably notice that's not 2 in the power of n. 2 in the power of n would be 2048, or the next number is 4096. But the way, the reason is there is 2,304 samples. There is a fairly clear reason for that. You can take those samples and divide them into 9 shorter chunks, which are 256 data points long each. And 256 is 2 in the power of, can do math in my head, in the power of 8, I think. Once you have 9 those chunks, each 256 data points long, you can do spectral analysis on each of them and then average them, thus reducing the noise. There's the WelCH approach to spectral analysis. This is what Waverider does as a standard. We played around when processing the data. We do the processing from the raw data sets. And in some cases, mainly we follow the Waverider's approach. In some cases, we when we needed higher frequency resolution, we would do, it is still WelCH approach, but we would do 512 data points long, and we'll do an overlap of 128 data points to get a few spectra that we could average and just reduce the noise. Although higher you go, more noise you'll get, higher in the number of data points you're dealing with. As you remember, fast Fourier transformation is switching from time domain to frequency domain. So even though you have 30 minutes of observations, you can't get spectral parameters any parameters for every minute in those 30 minutes. You need to take the 30 minutes and then calculate 1 spectra and 1 set of parameters. So there's the Waverider. There's the way we deal with the Waverider data, and I'll go back to that again, to the processing. I just wanted to show an example of how we deal with the raw data. A few things that I wanted to go through, 2 very important steps. Again, they have to be fully documented in case of EMAC. That's quality assurance and quality control. Often they are used interchangeably, which isn't strictly speaking correct. But if you look at the ISO definitions of quality assurance and quality control, they're not very helpful. So quality assurance, part of quality management, focused on providing confidence that quality requirements will be fulfilled. Quality control, part of quality management, focused on fulfilling quality requirements. Not helpful at all. It doesn't really provide a good grasp of what it actually is. But the giveaway here is the bit which says will be. So quality assurance is what steps you can take to make sure that the measurements that will be done will be up to scratch, will meet the criteria that you want them to meet, will be over really high quality. And that's on the preparation stage, during the measurements, and so on, so on, so on. Quality control is post-deployment, post-data collection bit. At that point, you take the data and make sure you control that it's of high quality. You get rid of all the errors you can find in the data, and you're confident you can use it now. So another giveaway is assurance. So you make sure that the measurements will be okay, and control. You control after you collect the data. I put a very useful resource here called CARTOD, Quality Assurance of Real-Time Oceanographic Data. That's a set of standards that could walk you through how to process oceanographic data. It's very, very good and useful. So I'm probably going to delve a little bit deeper into quality assurance and a lot deeper into quality control. There are a few important steps with quality assurance, important things to remember. It is very important at the start of the measurements to identify the requirements of what we're measuring and why we're measuring. because that will guide the choice of equipment and the choice of the deployment solutions you're going to use. I mentioned infragravity waves a little bit earlier, which have a really long period. These are the waves that surface buoys would struggle to identify because they're set to measure the relative displacement around zero, but a lot longer signal would be naturally filtered out. So in that case, you might prefer to use a pressure sensor if it's a fairly shallow enclosed bay and you know that infragravity waves might be a problem, and that's specifically what you want to measure. You might use pressure sensor on ADCP to do that type of measurement instead of a surface buoy. Similarly, the physical deployment requirements, as I mentioned, the surface buoys are very sensitive to the moorings and to the currents. So if you're deploying in a deep water, you might want to use subsurface false bottom, like on a picture here. This is a surface following buoy as well, a fibrous wave scan buoy, which is often deployed with a false bottom in a false bottom configuration. Similarly, when measuring waves on our tidal side, which is important to know as well for the tidal machines to know the loading on them, we can't use surface buoys because the currents there reach 4 knots at peak quite easily. Sorry, not 4 knots, 8 knots, 4 meters per second, which means the surface buoy would spend most of the time underwater, flooded or not measuring anything useful. And also it is important to use reliable equipment, which has a good track record in the industry and have been used quite a lot. Just because by the time you get to use it, quite a lot of bugs will be dealt with. A few more steps. It's the equipment needs to be routinely maintained. That's a good practice. In our case, it's again a requirement that we have a schedule and to look out at the equipment, change the O-rings, add some, change some parts, bits and pieces of the instruments. All the documentation, software and firmware have to be up to date. Often you would see, often some bugs will be discovered and the manufacturers will sort them out in a software and or firmware. So it needs to be kept up to date. Where possible, calibration has to be done routinely. Before deploying, there are a set of pre-deployment maintenance and checks that needs to be done. Again, they're recommended by the manufacturers. People who know what they're doing should be involved. So trained, experienced staff, at least overseeing. And of course, biofouling is quite important in some parts of the world, especially. When it comes to EMAC, so quality assurance is ingrained in some of our standard operating procedures. That's the set of documents which govern what we do. And those include routine maintenance of equipment, how often we do that, how often we look at the, when we change some bolts out, change the O-rings out. There are forms which walk us through pre-deployment checks and maintenance. We have to have some qualifications that allow you to work with equipment and so on, so on. Calibration checks as well, they're all done on a regular intervals where possible with oceanographic equipment. That is part of our of the requirements of an accredited lab, that you have all those things in place and you follow them. Moving to quality control, so that's done on the after the data is collected. You'll be surprised how often this step is overlooked while being very, very, very important. The thing is, it's not even that errors occur very often, but unless you do the quality control, you can't be confident that the data you're using can be usable. So, for example, you did wave measurements, you had a Waverider in water for a month, and then took it out, download the data, and didn't look at the data and used it for something else, any research, analysis, or for power performance, whatever it is, because you didn't check the data, the end result essentially is not valid because you don't know. There is no confidence that the end result is good because you haven't looked at the data before. It might have been absolute nonsense. It might have been measuring not more than 1 meter waves in Bilekru in Orkney through the winter, which never happens. So there's very, very important stage. Plus, there is always potential for errors, and they could come from the sensor itself, from the environment, from power failures or surges. A data acquisition system could cause problems. There could be just failure in data communication if you're using Waverider Boy, which is transmitting real-time data, and then communication drops for a little bit. You'll have just missing data. If you didn't do quality control, you'll keep that missing data in, and that will be that's not good. I put here wave quality control and processing workflow, at least the way we follow them at EMEC. We, generally speaking, you take raw data out of the instrument. Quite often it is coded. It might be a binary file, like in ADCPs. In most of ADCPs, it could be hexadecimal message, like with Waveriders. You need to convert it into something usable, into engineering values of the signal. So the displacement in case of Waverider. After converting the raw data, we do the quality control on the signal itself. So displacement up and down, north, south, east, west, and so on, so on. So we do quality control on the signal, and that's yeah. I'll get to that in a second, but from the quality control of the signal, we do the processing and switch from the signal to physical engineering values and to the spectra. There's the processing bit. And from then we do a second set of quality control on the parameters derived. And in this case, there is a slightly nuanced difference between the processing signal and processing the parameters. Because in case of parameters, you would be looking already on, do they make a physical sense rather than is it a good signal or a bad signal? So now you're looking more into underlying physics and what you're observing. Once that step of quality control is finished, the data set is finalized, there is a metadata created and it's saved for dissemination or the further analysis and usage. I'll mention in a second how exactly we do that at EMAC and what are the things we do there. So a few good practices for handling the errors when doing the quality control is we try not to alter the data to change the data. Instead, we use quality control flags, which are essentially, we add another variable to each of the existing variables. So for example, if we measured significant wave height for a month, it's 720 values at half an hour periods or an hour periods. At an hourly periods, it will be 720 measurements. And that's the time series of significant wave height. We create second variable, which is quality control of significant wave height, and it has exactly the same size. Each data point in quality control, in the quality control variables, relates to a single point in the significant wave height time series. And the quality control variable essentially contains flags. So once we look through the significant wave height and we find the data point which is bad, instead of changing that data point, all we do, we assign to the quality control variable, to the corresponding quality control variable, a flag which says this particular data point is bad. In our case, I've listed here the flags that we use. Is very close to what CDataNet uses. We just dropped a few of them. So we go 0, 1, 2, 3, 4, 8, 9. They have 5, 6, and 7 in between as well. Different organizations have different systems of quality control flags. They're different in BODC, in CARTOT, in CDataNet. We just picked up CDataNet, and quite a few things in what we do are aligned with CDataNet requirements. The way we deal with the quality control of data, there are quite a few proprietary software that allow you to do it. They normally are provided by equipment manufacturers. So often they are manufacturer specific. Some are slightly wider, but what we needed to fulfill the requirements of our accreditation was for everything we do with the data to be fully traceable. So if we take the data we use for power performance, that we could trace back what was done to the data, to the very raw point, to the very raw data, to the instrument itself, and actually even beyond. So from the instrument, we can trace back what the quality assurance steps we took. So to make sure we can do it, and to make sure that the quality control tool that we have includes also not only Waveriders but also ADCPs and so on, we decided that it probably makes more sense to develop our own software. We called it IMPACT, Integrated Meta-Ocean Processing, Analysis, and Quality Control Tool. And it takes you through that workflow that I showed earlier, from the raw data to the very last finalizing and saving in a format for dissemination. For the whole that thing is taken care of by the software, which also automatically produces an audit trail of what you've done to the data. And there is another manual process that we follow as well. That's just the software. It's not the whole process. The whole process is described in a number of standard operating procedures, in the forms that we have to use, and so on, so on, so on. So it's a core bit, but not the whole of the QA and QC that we do when we collect the data. Plus, one of the requirements for that software under our accreditation is that it's fully validated. So we had to test it as much as we can and produce the validation report showing that it does what it's supposed to do. A few examples of quality control of signal. If you remember, we do raw data, then quality control of the signal for the Waverider. There are a lot more steps. I just pulled out three examples. One is finding the missing data and flagging it, so it's not used further down the road when you're doing the processing. Looking at the range of the sensor itself, we know the Waverider sensor has a limit from -20 to 20 meters in HEAF. So if you get anything below or higher, it has to be flagged as bad. And looking for spikes, they occur in oceanographic data quite often. That's just a rapid change in the measurements, which is unphysical, needs to be flagged. You can see I'm already at 45 minutes. I wanted to finish in 45, but still quite a few slides to go. So I'm going to speed up a little bit. So with Waverider quality control, in the processing of the signal data, well, the processing bits will, the processing bit, sorry, we've got quality control of the signal and quality control of parameter. In the middle, we have processing. With processing, as mentioned, we'll calculate the spectra. There are a few clever things we could do if we have bad data in our signal time series, such as, I know we say we shouldn't alter the data, but at this particular case, we probably could fill in the gaps if they're very small, either with zeros or maybe some interpolation. If the data is bad in one part of that signal time series, what you could do, instead of using 9 spectra and calculating the average, you could say use 8 and drop the bit, which is bad. Calculate the average. Normally we would flag it as probably good, or if number of spectra is really low, we'll flag it as probably bad. And then derive all the parameters that we need, spectral and so on, so on. After that, we need to do QC on the parameters. We'll get there in a minute. With ADCP, wave QC and processing, I think I'll leave that bit. The process. So if you remember that we get waves based on 3 measurements, either pressure or surface tracking or velocity. So I'll leave the velocity alone because that's the processing you would normally do for the current data, for the current measurements from ADCPs. Pressure and surface tracking, you would do the same processing on the signals as you would do with the Waverider. Just look at this, the spikes and so on, so on, so on. Parameter quality control is slightly different because now we look at the physics behind and the parameters, what they include. Normally, if you've done a good quality control on the signal side of things, the parameters you would get after processing would be fairly clean. There are just a few things that you need to look into and make sure that they are correct. You would still do spike and rate of change quality control, but need to be very careful because now some of the spikes could actually make sense. So like, for example, here, the peak period, which within half an hour jumps from 8 to 16. With the signal quality control, you'll flag it as bad straight away. But in this particular case, it's just a case of the one of the C state, which has two peaks. One peak was higher at one time step. At the next time step, the other peak became more dominant, and the peak period or peak frequency just jumped from one to another. It makes perfect sense physically. It just doesn't look pretty on the graphs. A few other things we would look at, for example, is maximum individual wave height and significant wave height ratio. Normally it should be between 1.8, 2.2 roughly. But again, need to be very careful not to discard something interesting that came through, such as, for example, log waves or whatever it is. We would also look not only at parameters, but on the spectra and look at the ratio of the energy in the low frequency part of the spectra to make sure it's not too high. It's all the recommended practices telling you what to look at. I think I've got only 2 slides to go, so I'll try to wrap up. One of the important things that, again, is missed quite often is the metadata, which is the data about the data. Who collected, when, what, where, and how, and so on. Without the context, data is essentially unusable or at least not reusable. But the thing with metocean data, waves in particular, and currents and whatever it is, that it is completely replaceable. So you can't measure in the same place and at the same time. So you can go to the same place, but it won't be same time. That's why it's very unique data set and it needs to be looked after. So if somebody gives you just a row of numbers, a column of numbers, you can't make anything out of it, like on the plot here. If I look at it, I would say, it looks like wave period to me. But then when somebody tells you the units, you can understand that it's probably wave height. And then the next question is, what type of wave height? There are like 4 or 5 definitions I can probably come up with right now. Significant wave height. Then you look at the times and you need to understand what is the format of the time. So this is all very, very important for the data to be reusable, because it takes quite a big resource to collect the data. And you don't want to collect it just for your specific research or work. You want it to be reusable for others as well. And this is absolutely a crucial bit. There are different metadata formats. We have our own, which is based quite heavily on British Oceanographic Data Center's metadata format, but there are CDataNet, MEDIN, and so on, quite a few as well. Almost last slide. What I'll do probably here, I'll just point you towards a very good resource, datatree.org.uk, which goes through best practices for data handling and takes you from the creating data up to reusing the data. Very useful. It's UK Research Council, but it's applicable wherever you work. It doesn't really matter. It's the good practice to deal with the data. Yeah, maybe a couple of things to mention from here is it is very important to attach license to your data, even if you're making it available to everyone to use for anything. The license will let them know that this is the case for the data, and plus will dissolve you of any liability for the data. And the data, our software is based on MATLAB. So all the internal data processing is done in MATLAB binary data format, but it's not the best format to disseminate the data because it's proprietary. So when disseminating the data, we use NetCDF, which is very popular with meteorologists and oceanographers. So we have a module which converts between the two to be able to provide it to others to use. Okay, so the takeaways, that's my conclusions essentially. It's important to know the scope and the requirements, because the choice of the setup of the equipment for the wave measurements will be based on that. Most of the measurements we do are based on surface buoys or acoustic Doppler current profiles if we're measuring currents in follow-ons in our Tidal site. Without quality assurance, there is a high risk of not collecting good data. Without quality control, there is no confidence in the accuracy or the usability of the data. And yep, data handling practices are very, very important, because essentially this data is replaceable, whatever we collect. Okay, thank you very much.
Thank you, David. We already have quite a few questions for both Francesco and you. I will start with some of the questions that have been given by the speakers. So the first one, I think it's for both, especially maybe for David. Are there any criteria to select or assess a test site location except the wave condition?
Quite a few, yes, and they are not only environment related. When it comes to environment related, you would probably want to be away from strong currents if it's a wave test site. And also closeness of different ports for the marine operations, easiness of consenting of the location. Depends what you want to do. If it's just the test wave energy converter without grid export, then you don't need a grid connection. But if you want to test it for the grid export as well, then you probably do need subsea cables and so on. So there are quite a few, quite a lot of things to look into. I think there are a few test sites around the world, but it's quite hard to build one from scratch.
Okay. Yeah. This one for Francesco. What are the kinds of risks that we can find in a commercial project and that we don't face in TRLs 6 and 7 in test sites?
Okay, yes, this is a good point, because as far as we consider the classical conventions behind the definitions of TRL, for instance, the one that I introduced that was developed by IES Ocean Energy Systems, when you move from 7 to 8, 9, you are moving to the real device that is going to perform as a commercial scale device. So this means that is like you move from the nursery, which can be, for instance, the EMEC beginning scale, but also the full scale site, into some place which was not designed to host developing devices. Because, of course, when you want to deploy a device, maybe you look for the best tidal results or wave results, and not because of the existence of a supply chain all around. And this is what can make a difference, because when you move to TRL 8, 7, 8, and then 9, of course, for instance, there are issues related with the duration of testing, which means that you might have unexpected events because of failures, damages, fatigue, for instance, impacts because of debris, fish, and so on, or eventually issues related with the grid connection, because grid connection is completely assisted when you are, for instance, testing at EMEC. But when you move to higher TRL, of course, there are issues related with the design of the substations, for instance, or even more if you are testing a cluster of devices or an array. So is another big jump into the real world.
Okay, thank you. Going back to David, how do you choose the sampling frequencies? Is there a reference frequencies spectral analysis?
Sampling frequencies are often recommended by the equipment manufacturers or are provided. I would say for wave measurements, you would want to be at least 2 Hertz to sampling at 2 Hertz if you can't set up your sampling frequencies. 1 Hertz is probably an absolute minimum, because that will allow you to determine waves which have period of 2 seconds, taking into account Nyquist frequency. So yeah, probably 2 seconds or higher, 1 second if you have to.
A bit related to sampling, I wanted to ask you one question. When we're moving out into open sea, and when we're talking about wave farms, not just one device, is there any kind of recommendation, because we know that any kind of farm, whether it's offshore wind, wave, or tidal, it's going to occupy a huge area. So is there any kind of recommendation of how many buoys you need per area, per unit area, or is it just in general you normally put on the most extreme points and then just model in between?
Yeah, I think it will be site specific. If you have say a quite, if you have a drop on your site, where you go from deep water into shallow water, what you would probably want to do is to measure something at the deep end and then something at a shallow end to make sure that your model takes into account all the effects correctly. But yeah, model will probably be your main source, but it will have to be ground. You'll have to get a ground truth for it.
Okay, thank you. Another question also for David. In terms of economics and performance, what observation methodology is better according to your experience? And would swan propagation model be enough to get accurate climate data to face an investment on a wave farm? Or would we always be needing to confirm the model data with real-time data from the observation?
I'll start from the last question. Definitely always would need some observations to confirm. You could even see it in the wind industry. Just based on the model data, you will not get any wind resource assessment. Does require deployment either of a LiDAR or of a map mast or something to ensure that the data model data you're using is correct, as close to the truth as possible. In terms of economics and
regarding that, do you know how long do you need to have in situ observations? Is it 1 year, a few months?
I would say so. The IC standards require at least half a year. I would say probably a year, just to make sure that you capture all the seasons. Longer, better, of course. Yeah. In terms of economics and performance, it really depends on the location, on the site, and what we want to get out of the measurements. I think by default, probably Waveriders, the wave buoys, not specifically Waveriders, wave surface buoys, might be the best option. Oh yeah,
sorry, I was muted. Sorry, going to the next one. Can you please discuss briefly the standard in energy power consumption levels of metocean gathering systems?
It's fair. It's not too bad when we're talking about wave and current measurements. So wave buoy would probably last quite long with the batteries on board. Most of them come with solar panels, and they could last for a really long time. So we're talking months to years. EDCPs, yeah, depending on how you set them up. Yeah, if we're going to LiDARs, which is sort of metocean as well, well, it's probably wind. Then the power consumption is completely different, really, really high.
This would be more related to offshore wind that are moving farther into the sea and into deeper waters. Do you know which is the limit that we can actually have? Because you talked about the false bottom. So probably we would have to do that. But are we talking to use that false bottom when we reach already 100 meters, or we're talking much, much more?
It really depends on the buoy itself. So the manufacturers will provide you an advice. But I think over 100, 200 meters from the top of my head, you would probably use a false bottom. But you can go with those buoys as deep as you want, 4,000 meters, easy.
With the communications, there's no issues even when you're, I don't know, 20 kilometers or much, much farther from the shore?
It depends. If you're using satellite communication, and satellite communication is very limited, so what you would get is the spectral parameters calculated on board of the buoy. But you can go then anywhere in the world. The buoys we deploy at EMEC, we have radio link because we want to get the raw data through rather than satellite, and we are limited to a few kilometers.
Okay, thanks. Going to the next one, do you advise using a device arrangement like several types of devices, buoys, ADCP or others, or only one type of device to obtain the data?
If possible, I would go with more. If you have an ADCP, if you have a Waverider and then you need to measure currents in the same location, I would set up ADCP to measure the waves as well, just so that you have a contingency. Equipment tends to fail, so it's better to have a contingency.
Probably I'm getting into the session for September, but have you ever used the buoy and at the same time measured acoustic, taking acoustic measurements?
Yes, not at EMAC, but I have done it in the past with a ADCP mounted on the buoy at the bottom, looking downwards. There are some things to be careful about, just because the buoy is designed to move a lot with the waves, while the ADCP you want to keep as straight as possible, so it doesn't. Further you go away from the buoy itself, more the swing of the wave currents you're measuring. But there are ways to deal with it.
But acoustic measurements more related to knowing how marine life is around the area. Is that normal to combine?
You could deduce something from the acoustic Doppler current profilers. I'm not sure I came across measuring for the environmental biological things. So you could get that type of information from ADCPs, somewhat some hint of it. I'm not sure I came across using something like passive acoustics or whatever it is from the buoys. I don't know why. I've never looked into that, but there probably is a good reason.
Yeah, don't worry. I'll contact you later. Okay, so moving to another question. Is there any specific taxonomy in the scientific community for waves, wave data base files, so that we're all able to exchange files on an easier way?
Yes, there is. So there are a few attempts to do that. Some of the databases would have a standard way to store, say, wave data or whatever it is. So the one we follow is CDataNet, which have their own format, and they have actually two formats. One is a plain text file, ASCII file, which you have to write the data in a certain format. One is NetCDF, and we follow NetCDF just because our files are quite big. But there are, so CDataNet and quite a few. I just can't think of just from top of my head, but that's the one we use.
In any case, just for everyone checking the sessions, if we have any other comments or questions that we're not able to respond during the time of the sessions, we will try and also respond them in text and include them with the presentations and everything that we upload into the website. So we have also two more questions. Could you talk a bit more about the appropriate conditions to deploy a wave buoy over an ADCP and vice versa? In terms of quality, data quality for waves, is one superior to the other?
It really depends on the conditions, on what you're trying to measure. There are limitations, yes. So there are limitations for wave buoys. They can't go in places with high currents. So in our Tidal site, to measure waves, we would use ADCPs. Similarly, ADCPs have their limitations. As I mentioned, if you're interested in directional waves and the location is fairly deep, or your ADCP location is fairly deep, then the cutoff frequency for the directional waves you would measure is quite high. So you would miss quite a bit of important information. So in that case, you would probably prefer Waverider to ADCP. In terms of quality, generally speaking, probably wavebuoy is a better way of measuring waves, but ADCPs these days are getting a lot better, especially with the vertical beams. You could collect really good quality wave data. So it really depends on where you are and what you're after.
Okay, one more question from the attendees. Are there currently any challenges regarding the amount of data to be collected for a specific project, and the amount of data that also can be processed and analyzed? Any changes in the future?
The amount of data to be collected, I guess it's always the challenge, especially when it comes to the waves, because of their sort of random nature. You need to collect a long enough data set to draw any conclusions. So you don't always have a year of time to collect the data. And the problem with metocean data is you can speed it up, right? If you're doing survey, you can bring a lot of boats and do the survey faster. you can speed up metocean. You have to measure for a year. I think that's probably the biggest challenge you would come across. When it comes to processing and analyzing, it's a lot faster. So I don't think the challenge would be there. Challenge is actually collecting the data.
Okay, I have a couple more questions. Now that we all know that MaRINET unfortunately is ending, MaRINET2, do you have any other projects, open projects, or that will be open in the future for installations and researchers to test their devices in EMEC?
I'm not 100% sure, just because I'm more of a metocean side of things. I know there are a few projects ongoing right now, Ocean Demo, for example, which was for the developers to come and test. I don't know if there are any more calls on Ocean Demo. I'll probably need to check with our team. Other than that, it's probably worth to chat with our commercial and project management teams.
They also mentioned the issues and risks with commercial projects, especially where there are a lot of countries, and we have a lot of participants from Latin America and from other countries that don't have yet testing facilities. So they don't belong to the European Commission or European Union, so it's also more complicated to bring a device across the whole world to test. But when would you recommend these installations, and is there any recommendation to give them on which type of devices and sensors should they start installing first, and which ones are like secondary or additional sensors that you will need?
In terms of measurements, wave measurements and stuff. I think as soon as possible, whenever you know where your site is, where your site is, I would straight away stick something in the water, just because you can speed up metocean. So you need to collect to build up that data. So as soon as possible, put some metocean stuff in. That would be my advice.
We're getting a little bit more questions. Is wave data is location or geographic condition dependent? I think so.
It definitely is, yes. Waves are very different in Orkney and say in Black Sea or Mediterranean.
Maybe what he wanted to ask was how far we can go with the modeling. For example, as you mentioned before, if you have a wave farm, you should measure on the highest depth and on the other extreme, just to have a nice simulation. How far can we go into accepting that the measurement that I had in this spot will be representative of something that is, I don't know, 2 kilometers away?
Yeah, it is very location specific, so you would need to have someone to look into it and then advise where to stick things in.
Okay.
Equipment.
Another question, is there any nice site with raw data for determining the significant wave height? I need to use teaching determination instead of getting significant wave height.
Yes. Oh no, raw data.
Well, I don't know if he by raw data if he means in situ or if he's talking about satellite data.
Maybe if you can drop me an email, we can have a chat. That might be easier. Yeah.
Okay. Another one, what is the range of error between lab and actual data of wave characteristics?
I can't give a number straight away. I don't think I'll be able to. I never looked into it, to be honest. I came across some papers, but I wouldn't remember. I don't know, Francesco, is there anything you could?
Yeah, this is really a good point, because in principle, of course, at laboratory scale, by the way, I'm working in an institute where we have laboratory scale facilities. And for instance, we have wave towing tanks where we try to reproduce the wave climate that is typical of different geographical conditions. So this is back to one of the questions before. There are in the literature wave spectra that are typical for different oceans and seas. So you can try to reproduce these wave spectra using a wave maker. device. Of course, the quality of this reproduction at laboratory scale is something that is questionable, because I would expect that the real physics of the wave climate is something that goes beyond the spectra that are from the literature. So I think that in theory it is possible. You can get close, but then reality, of course, is much more complex. I don't know, David, you have been never involved in such kind of comparison between simulated wave patterns at laboratory scale and real set conditions?
Yeah, well, possibly, yeah.
Sorry.
Possibly most of the comparisons are more related to the satellite data and the in situ data, right?
Yeah, I think there was. So I personally haven't been, but I know FlowWave, the test tank in Edinburgh University. They reproduced our tried to reproduce conditions at Belay Crew using our Waverider observations. I don't know what was the result. I know they got really quite good results, but I don't know. I wouldn't put a number on it.
Yeah, for instance, at laboratory scale, a problem can be about directionality of waves, which is not that easy to reproduce. But as far as the wave spectrum, maybe this is feasible.
Okay, thanks. We have 2 more questions. In order to analyze the swell or seas in the directional spectrum, do you have any preferred methodology?
I muted myself. No, there are quite a few partitioning methods. I don't think I have any preferred. We just choose the one we works best. Yeah, I can't remember from the top of my head, but I used the watershed methods. Can't remember now. But yeah, I picked up one and used it.
We can add additional information later. Don't worry.
Yeah.
Okay, and the last one, you speak about typical wave spectra following regions of the world. Where can we get information about this?
I'm not sure I mentioned typical wave spectra for region. Some of the standards might contain information like that. For example, DNV's recommended practice is C205. I don't remember if they have at the end regional information or not, but it might be the place to look at. Another one is ISO 19001. It's a metocean standard in petroleum industry. At the very end of that standard, the 2015 issue, you would have a whole appendix related to different conditions in different regions. So you would probably find some interesting information there.
Okay, thank you.
Yeah,
so
thank you.
With this, we're closing the first part of the session. We'll have now a short break and we'll be coming back at 1:45, okay? In about 10-12 minutes.
Okay.
Okay.
Thanks very much. Thank
See
you.
you soon.
See you then. allora.
Hi, Francesco. Hi, Muhammad.
Hi.
Sorry, Safi.
Can I speak now?
Yeah.
Okay. So firstly, thank you.
Give me 1 second that I'll introduce both. We will now start the session on in situ observations Tidal. Then we will have a short Q&A, and then we will finalize with a recap from both Francesco and Safer. Dr. Francesco Salvatore from CNR is a senior researcher. He has a master's degree in aeronautics and PhD in fluid dynamics. He's focused on marine propulsion and marine renewable energy systems. He's also working on computational models for the analysis and design of marine propulsors and hydrokinetic turbines. Dr. Sefer Rafiei, assistant researcher, he also has a master in energy engineering and PhD in electrical engineering from the Sapienza University at Rome. His research interests are focused on marine renewables, energy conversion systems, and especially on the power takeoff and control systems. Welcome both.
Thank you. Okay, could you share?
Yes, let's go sharing the screen.
Definitely.
Okay.
Yes, just go to presentation mode. Perfect.
Okay, do you have my screen?
Yes, it's perfect.
Okay. Good afternoon to me. So today I'm going to briefly speak about the tidal energy turbine and conversation technology briefly, and then the objective and scope of the field test. Then we will see together what is the exactly objective of the in situ observation and the methodology and instrumentation for this goal. And then we will see the data processing and quality control. And then at the end of this presentation, we will see the data presentation and analysis. So marine current basically could be classified in two types. One is the ocean current that's generated by the salinity and temperature gradient, and it's usually rarely exceed 1 meter per second. Despite that, the tidal current, which generated by the gravity forces between the Earth and the Moon and Sun, that could in some places that could exceed 5 meter per second, which is an interesting amount of the energy to capturing and producing the energy. So the tidal stream, which composed of the flood and ebb cycles, associated to cyclic variation of the tidal range, which is about the 6 hours and 12 minutes. As you can see in the in this diagram, the maximum and the minimum peak of the tidal velocity, which respectively called spring and nip, all happen twice at the 4 week, which is the month, which is the lunar month, and it's because of the moon position, about the moon position with respect to the Earth. And the other things that have to notice is the flow direction affected by the coastline and site morphologies and bathymetry. As you can see here in this other diagram, there's two types of the tidal range predictivity. One is the semi-diurnal, and the other is the mixed semi-diurnal, and actually there is a diurnal. So technology is to capturing the energy. There can be classified in a 4 type. The most, the well known of them is the horizontal axis, as the EMEC Atlantis. The other one is the vertical axis as a hydro crest. The other type is the cross flow axis, or RPC, which is also adequate for the river to energy. And the other is the kite type, which the famous of the things is the Minestro. So actually there is two kind of the support structure for the turbine. One is the seabed fixed as a sabella, and the other is the floating installation. So also for the floating installation, it depends on the how much is big the turbine scale. For example, for shuttle hydro, because there is the small turbine, there is the floating turbine cluster, and for the megawatt scale floating, can you see in the last pic? There is also this floating boat as the orbital power project. In order to characterizing the turbine hydrodynamic performance, there is four undimensional characteristic of this turbine. One is the kinematic coefficient, that's called is the tip speed ratio, and the other is the dynamic coefficient, which is the thrust coefficient and torque, that usually is for characteristic of the mechanical load inside the structure of the turbine, and the other is the power coefficient in order to analyze the turbine efficiency. So to present the power of the turbine, we can see here there is a two type of the presentation of the turbine, which is the power as a function of the rotational speed at a given flow speed. So as you can see, for every of the given flow speed, there is a 1 point of the maximum power point. So the red line show the maximum power point tracking condition. That's the sum of the control is using this condition to have the maximum power at the below of the power rating. So also you can see in this diagram the power as function of the flow speed, and usually it can be divided into regime. First regime is the below of the power rated or flow speed rated, and as I mentioned before, is called also MPPT tracking. And the second regime is when the turbine arrived to the past the rated flow speed, and the goal is to maintain the power in the rated value. And so you can see here that is the cutoff velocity. It's due to the mechanical load limitation of the turbine. So after capturing the hydrodynamic energy by the blade of the turbine, there is the power system, power takeoff system to transmit of this, to converter and transmit of this energy to the grid. So the power takeoff system, including of the mechanical drive shaft, that could be that could be with the monostage or multi-stage gearbox connected to the generator, or directly connected to the generator that's called the direct drive. And there is a generator which takes the mechanical torque by the shaft from the turbine blade and convert to the electrical energy. And there is the power electronic interface to adequate the frequency as required by the grid, that is usually is the 50 or 60 hertz. And actually there is the transformer to transfer the energy electricity from the located of the turbine to the grid inshore, so to have a less losses also. So here we ask what is the objective of the in situ monitoring. So in order to successful development and early commercialization, it's fundamental to know about the extreme effect of the marine environment on the device. So to assess devices' responses in the real operation environment, and actually once the tidal resource has been characterized. In this category, the resource and or devices interplay involves two complementary aspects. One is the device performance. That means how much it will be the energy output. So to knowing these things, it's fundamental to know how much is the flow speed, intensity, and distribution. The other complementary aspect is the device reliability. That's about the structural loads and the fatigue. These fatigues due to the fluctuation of the flow velocity of the tides. This fluctuation in the flow velocity is affected of the turbulence eddies and the underwater effects of the surface waves, and actually shear profile across the vertical column. Here there is an important message, that is the full characterization is beyond technical or budget limitation. So fundamental to determine a realizable test camping with effective output for data and users. So until here, we speak about a little bit about the devices, what is the tidal turbine, and we have a vision about these devices. Now we are going to know about the turbulence and waves, and I give the speech to the Francesco.
So thank you very much, Sepp, for this introduction. We felt that it was a bit important before talking about the monitoring of the resource for a tidal energy device, to contextualize the problem in terms of what we are installing in order to capture and convert in energy. That is why we made this preliminary review of the capturing and conversion technology. So we understood from Sepp's talk that there are two main physical phenomena that are relevant in order to characterize the behavior of these devices. One is about turbulence and the other one is about waves. Of course, David in his previous talk has told a lot about waves and the effects that they may try to concentrate on turbulence. Basically, tidal flows are characterized by strong variability of velocity, intensity, and direction. In particular, there are eddies that are generated by seabed roughness, boundary layer, bathymetry, surface waves, velocity shear in the vertical profile. All these velocity fluctuations have a significant impact on the tidal energy conversion device performance and reliability, as Sepp already anticipated. So it's very important to characterize the side flow in terms of turbulence. So let's try to find some common meaning about turbulence and important aspects related with turbulence scales. Turbulence means velocity fluctuations. Typically, we talk about eddies. Eddies is a quite general concept, which basically means the presence of vorticity and velocity fluctuations into the field. These eddies can have multiple spatial and temporal scales and 3D orientation, as for instance is shown in this sketch on the right. A rule of thumb is that spatial scales are typically less than 1/3 of the site depth, and as an average, at least for present applications, site depth is in the order of 40 to 60 meters. An important assumption is that large scales have a long time of decay, which means that we can assume that during the passage of large eddies, their shape, their velocity fluctuation is frozen in some sense. And this is a condition that is very frequently used in the elaboration of data. An important aspect related with turbulence is the energy spectrum that are characterizing the so-called energy cascade from large eddies to smaller eddies. And this is a well-known theory that is quite general and mostly due to Kolmogorov. As you can see on the right, there is a typical energy spectrum as a function of frequency, which identifies three main regions. One is the production region, where eddies are generated at low frequency at a large scale. Then we have an inertial subrange where the energy is moved from larger scales to smaller scales, and finally dissipation in very small scales. For tidal energy conversion devices, the inertial subrange, which means approximately between 0.1 and 0.7 Hertz, is relevant. And in order to understand this, we can put some figures about a possible conversion device. Considering, for instance, a 0.5 megawatt turbine as the rated power, this means that the rotor diameter is about 10 meters. The flow speed we can imagine is about 3 meters per second, and the design TP speed ratio is about 5. Well, in these conditions, the rotational speed of the rotor is about 0.5 Hertz, and the blade chord is about 0.4, 0.80 meters. These are time and spatial scales that will be relevant. And this brings to the characterization of these scales. This is something that is typically considered in the framework of providing metrics for the turbulence, because as it is quite obvious, turbulent flow is characterized by a tremendous complexity of phenomena, because in particular, as in the case of waves, of course, as we heard before, the velocity fluctuations have an inherent random nature. So a statistical description is required, and typically what is done is to decouple the actual velocity at a given point, a given instant, into a mean value and a fluctuation. Studying turbulence means to focus on these fluctuations. Of course, there is statistical quantities that are typically introduced in order to characterize these phenomena. The first description is given in terms of mean and variance or standard deviations. So you can see definitions. Please, it's very important to note that here, when we are considering site observations, monitoring measurements, we leave the area of continuous distributions and we move into the world of discrete sampled data functions. So a concept that we will see is very important is data aggregation, as we will describe later. So once you have defined the mean values and the standard deviation, you're ready to define a first important metric quantity, which is the turbulence intensity, which is again a global indicator of how much the field is turbulent or not. Next, if we move a bit further into the definition of turbulence flow characteristics, an important step is to introduce the Reynolds stress tensor, which is basically what emerges into the Navier-Stokes equations when you take into consideration the random nature of the velocity and pressure distributions. And as you can see in the Reynolds stress tensor, you have a symmetrical tensor where the terms on the diagonal represent normal stresses, while the terms ahead represent the shear stress. These terms, in particular the terms on the diagonal, are related with the standard deviation that has been introduced previously. Another important aspect, as we have considered before when we introduced the Kolmogorov energy cascade concept, is the definition of the kinetic energy associated with a turbulent flow. Of course, we have a direct definition where again we can find standard deviations involved, but there is another very important definition where the energy spectrum is considered. And the energy spectrum here indicated with E is basically obtained as a fast Fourier transform of the autocorrelation between velocity fluctuation, a given component of velocity fluctuation at a given time step, and the same velocity fluctuation in the same point at another time step. And the time delay is indicated with tau. This definition of temporal autocorrelation is fundamental because it allows to introduce two other fundamental quantities that characterize the turbulence metrics. The time scale, which is basically a finite integral of the temporal autocorrelation, and the length scale. The time scale can be considered as how long the flow field structures remain coherent to some extent, because since we are dealing with a turbulent stochastic phenomenon, of course, coherence is relative. And the same is about length scale. And using the Taylor's assumption in terms of frozen turbulence, we have a direct relationship between time scales and length scales. So why turbulence is important? Because larger scales are responsible for load fluctuations that affect blades and drivetrain integrity. But smaller scales can be even more dangerous because they excite high frequencies vibrations and can be responsible for fatigue loads, as indicated in this diagram. Another important aspect is that in the wake of a turbine, if the flow is highly turbulent, the energy mix is very important, and the velocity defect in the wake dissipates very quickly, as it is seen, for instance, by comparing what happens if we move from an intensity of 3%, turbulence intensity, of course, to 15%. These are results from experimental work at laboratory scale, but are very nicely. The problem is that if we have an array and we have a rotor operating in the wake of a rotor upstream, the amount of turbulence intensity is fundamental in order to understand how much the aft device will be able to extract power. And from this comparison between power coefficient in behind conditions with low turbulence, 3%, or high turbulence, 15%, you can see that the amount of power that is lost in the behind rotor is much lower if there is this energy mix that is induced, stimulated by turbulence. So this is very important. Is as much as possible the turbulent flow matrix. Of course, last but not least, as much as possible, we needed to characterize turbulence because these data from real-life conditions in a tidal site are essential to validate CFD models that are used at the design stage. Again, surface waves, the other physical aspect that may have a great impact on the performance of a tidal energy device. David told about waves as the energy source. Now we are talking about waves as something that provides a nuisance more than something useful. Of course, waves induce motions below the free surface that affect the operation of the device and perturb the onset flow for field. This is very important in terms of the quality of measurements that can be done in situ measurements, because of the difficulty to separate what is onset flow turbulence and what is wave-induced velocity fluctuations. Basically, why we have these velocity fluctuations below the free surface induced by waves is clearly seen by a very simple linear theory. Of course, the reality of a tidal site is nothing linear, but this theory, in a good approximation, provides an estimate of the velocity fluctuations that can be observed up to depth that are typically in the order of the significant wavelength, which means 10, 20 meters. And this means that these effects can be relevant not only for floating devices, but also for seabed fixed devices. And what is important, again, is to characterize wave-induced motions as respect velocity fluctuations related to real turbulence. This creates a lot of troubles in terms of data processing in order to decoupling these two effects. There are several techniques, for instance, coherence method. You can see references here. Coherence method is based on the assumption that turbulent structures are not coherent along the water column, while, as we see, for instance, by a simple linear wave theory, wave-induced orbital motions are inherently coherent. Of course, the best practice is different. Avoid as much possible waves during flow turbulence measurements. And this is why, of course, for instance, in the characterization of a tidal energy conversion device at initial stage of deployment at sea, is better to operate in a tidal site where the wave climate is relatively mild. Okay, so we have understood the importance of turbulence and the importance of wave forcing from a physical viewpoint. Now, Sepp, please tell us something about how to measure these effects in water.
Okay, thank you, Francesco. So the instrumentation is really an important topic because it's the main devices to take the data and give this possibility to take data processing. So there is a variety of the flow, velocity, and actually fluctuation. One of them is the electromagnetic induction sensors, which use the property of the electricity inductivity of seawater by making the magnetic field inside the small volume of the sampling and changing the flow velocity, measure the flow velocity. The other flow velocity sensors is the piezoelectric, which is with the solid surface. It's usually is the ceramic, and work with the mechanical strain. by the changing the pressure of the flow velocity, and is commonly used in aerospace industry. The other sensors is the hot wire or field, and actually pitot tube that's work with the Navier-Stokes principles, and a lot of other sensors. But the common drawback of all of these sensors is the single point measurement. So in order to have the 3D dimension of measurement, it's required multiple unit of the sensors. And actually, all these sensors is effective in a laboratory test environment and twin time test, and is not adequate for the field test. The other kind of the sensor is the acoustic Doppler sensors, which use the Doppler shift resolution from the scattering of sounds by suspended particles in the water. So in this kind of the sensors, it's need to assumption the velocity of all these particles is the homogeneous. And another thing is spatial profile is achieved by knowing the speed of sound in seawater and controlling the sample timing of the reflect acoustic pulses. The main advantage of this kind of the sensors is these sensors can measure the flow remotely at the significant range from the devices. And actually we can classify these sensors in two types. First is the acoustic Doppler velocimeter, that's called ADV, and second is the acoustic Doppler current profiler, called the ADCP. As also David mentioned, these kind of the sensors in order to measure the wave characteristics. So acoustic Doppler velocimeter is the converging beam type, and actually there is the point-wise of the sample volume close to the devices in order to measuring the intensity and direction of the flow velocity. So there is one acoustic transmitter which send a beam of the acoustic signal at a given frequency, and there is 3 to 4 acoustic receivers record the Doppler shift in the frequency of the scattering acoustic wave. In order to calculate the direction and amplitude of the flow velocity, it's required exactly the characteristic of the transmitters and the sampling volume are actually the receiver position. So that's need all of this detail to processing exactly the data that's becoming recorded by these devices. Usually these devices, because of the smaller control volume and high sample frequency, has the best performance for the turbulence measurement respect to the ADCP, because the frequency for these devices is the 64 Hertz, but the ADCP I will be show after, it's between the 1 Hertz until the 2 or 4 Hertz. But the significant drawback of these devices, this device is the single point measurement. So in order to have the 3D measurement of the flow velocity or turbulence, that's required the multiple unit device. And so asking these multiple devices required a complicated mooring and subsequently correction. The second acoustic Doppler sensor is the ADCP, which is the diverging beam type. That's the diverging beam type, give the possibility to measure current speed and the direction at the interval through the water column. Usually there is a 3 to 5 piezoelectric transducer which transmit the sound signals and receive itself. You can see also in this picture the gray arrow shows the transmitted acoustic signal, and the dashed black arrow represent the reflected signal. The deviation of this beam, it's between the 20 and 30 degree. That's give exactly this possibility to have the intervals through the water pond, but by going increase the distance from this from the unit, the accuracy of the measurement becoming low. Also, the number of the beams and actually units determine how many flow of fluid details can be characterized. For example, one unit with 4 beams can measure 2 Reynolds stress, but using the 2 units of these 4 beams, ADCP could be exactly measured all 6 Reynolds stress. So the significant advantage of this technology is relative ease of configuration and installation on obtrusive flow measurement. That's lead to this kind of the measurement devices becoming the defined bed-mounted current profilers as the perfect current velocity measurement device according to the IEC standard. So the question is how is the installation for the sensors? So there is the variety of the type of the installation. One is the seabed fixed, buoy suspended line, boat mounted, and subsea grinder. So why this is so important? So when the data becoming acquisition with this instrument, in order to data processing, it's need to know the sensor position and actually sensor movement when the data come register. And so when we are going to the data processing, we have to know these things and remove from all the data recorded. So in the seabed fixed devices, we can to simulate simultaneous acquisition at the limited spots, while for a vessel mounted device allow for high resolution but not simultaneous. There's a difference between the 2 cases of the structure installation. At the present, there is not any single instrument system to provide them completely multi-scale measurement of the tidal flows. So as you can see in this picture, there is some configuration of the multiple unit sensors to have a fully data of the flow fluctuation. In this case, this project, Remark project, is the REDA project. So that they use 3 single bed acoustic Doppler profiler and the vertical oriented Nortec acoustic wave and current profiler, that's called the AWAC, and 2 diverging beam acoustic Doppler current profiler. One is the upstream of the turbine and another in the rear of the turbine. So the other things that I wanted to mention it is the according to the IEC standard, the inflow measurements are taken at an upstream distance of between 2-5 equivalent diameters from the rotor plan. As you can see here, it's the distance is between the 60 to 100 meters. So after speak about the instrument, it's important to speak about the data collection. Here you can see one of the remarkable project, that's the Sabella turbine in the operation phase. So when we are going to the collecting the data, of course, we have a lot of number of the challenges, which I sorted here. Non-controllable condition, non-repeatable condition, stochastic behavior of the physical properties, a statistical approach required, test subject to metocean condition and tidal phases, and limitation due to the time and budget, and finally attention to safety and impact. So the message is the fundamental to follow, accept test protocol and standard procedures for all the phases of the test program. So in order to collecting the data, we have to recognize some condition. So where we want to go into the measure the flow velocity, one is date for the deployment, or we want to go into the measure it around the device already we have it. And so we have to measure three things. One is the mean unperturbed flow. That's the instrument position upstream of the device at the suitable distance, as you can see Lx in the picture, or aside at the distance Ly beside the turbine. Or the second is the vertical axis profile across the line A, you can see, which is the aggregated data on spatial bands. Layer close to the seabed and free surface are removed. And the other thing is the turbulence metric across, again, line A. That is the present the turbulence, intensity, STD, integral, length, scale, and Reynolds, and stress components. So when we are going to the doing the collection of the data, of course, the approach used to collect the flow velocity data reflects K condition. Here, I sorted in a table the condition and requirement, and in the right of this table, the best practice. So when very different time scale involved when we are going to the data collection, so that will be weeks to describe seasonal tidal cycling variation, or the seconds to resolve all the relevant turbulence scales. So the best practice for this case is the tidal flow data collection should cover at least 4 or more weeks. Other cases is when the instrument provide time signals as sampling data at given frequency. So the best practice is the sampling frequency of 1 to 4 Hertz recommended. As I mentioned exactly about the frequency of the ADCP. The other cases is the stochastic phenomenon observed. That will be data binning into time period and decomposition into mean and the variance or standard deviation. So the best practice is quasi-stochastic condition achieved with the 5 to 20 minutes time period. And the last one is spatial variability is resolved by binning data into a limited number of slots. And the best practice is for vertical profiling, spatial bin of the 0.5 to 1 meter suggested for megawatt scale devices. So The other thing have to be considered is the device performance data. So it is fundamentally to know how was the turbine performance during the operation. For example, electrical power upstream of the connection to cable, rotor rotation speed, loading and strain sensor on blades and other components. That's exactly can recognize with these sensors how much is the thrust coefficient, device yaw or pitch angle, and the device status. That means when we take this data collection, turbine was in the operation phase or it was the free wheeling or in parking mode. And it's important to know the status of the ocean condition when we take this data collection. For example, wave climate, that's a significant height, period, and direction that could be affected all the data. Tidal cycle, it was in the ebb or in the float. The other things, ambient temperature and pressure, that's exactly changed the flow velocity because of the temperature and pressure. Quality indicator and confidence level for the correct position of all the sensors. So all these things is fundamental for correct analysis. As you can see, for example, here in the diagram, the blue line presents the daily velocity of the tide, and the black signal show the float or ebb of the tide. So the number 1 showed the float and 0 showed the ebb. And the red line showed the turbine heading degree, how much was the degree of the turbine. So I'm pass again the speed to the Francesco to how the data processing.
Okay, thank you, Sepp. Of course, thank you for leaving to me the part of the job that creates headaches, because it's very nice surfing to offshore to deploy instruments, to collect the data, to check, but then the problem is what to do in order to get meaningful data. And this is the realm of data processing. There are a huge number of rules that we need to follow. First, of course, we have to remember that we start from a stochastic phenomenon that is described through a sample of data. Okay, this affects, of course, the approach, the methodology we use in order to process data. Averaging is necessary to pass from the stochastic distribution to something that can be managed in terms of data processing. And this is performed continuously by meaning sample the data into time slots. This is what we can see here, where you see, for instance, velocity component during a head or flood cycle. Binning in time means to separate sample the data into small slots. As Sepp already anticipated, there is an approach to limit this duration to 5 to maximum 20 minutes in order to ensure a stable mean and variance, of course, based on the assumption that the phenomenon is quasi-stationary. But of course, you cannot enlarge too much this time bin, because otherwise you would measure something that is really changing, because the tide is changing actually. So there are rules, as for instance, the suggested sampling frequency, which is between 1 and 4 hertz. And this allows to get mean values and standard deviation. Similarly to time binning, there is also the necessity to aggregate data in a space, and this is, for instance, because, as you remember, in a Tidal site, we have a vertical velocity profile. So the intensity of the onset flow is changing very quickly from one layer to the other ones along the vertical column. And also here, the binning strategy allows to organize the data. Typically, these vertical columns are binned into 1 meter depth bins. As already mentioned, SEP, typically the layers closest to the free surface and to the seabed are not considered. Data from these bins are used to evaluate mean and variance quantities. Of course, the spatial resolution of sample data is not related to the slide dimension, but depends on the instrument used. And as we already heard from SEP, the control volume can be in the order of cube centimeters for an ADV, while larger volumes are typical for diverging beams ADCPs. Data processing. First, we needed to make some pre-filtering in order to blank data from positions close to known interfering obstacles, shadow regions, proximity to instruments that can create wrong data. Filtering is also applied to remove non-relevant data or conditions that are expected to determine poor quality measurements. This is, for instance, the case with slack water times between ebb and flood. This is much dependent on the site. Large waves, because we mentioned that for tidal flow characterization, waves are not that welcome during tests. And velocity samples, as I mentioned, for layers close to seabed and to the free surface. So we have made this preliminary filtering. We find that there are still outliers, which means data that occur outside the expected range of values and should be excluded for the calculation of the mean value and variance. That exclusion is a bit tricky because there is a risk to remove real turbulent flow fluctuations, as for instance, in this case, we see a reasonable distribution of fluctuating velocity. Then, of course, we see that there are some outliers, and there are cases where the measurement is not that clear if it's an outlier or not. And in order to characterize, to automatize the sorting of outliers from non-outliers, there are a lot of techniques, like, for instance, the minimum absolute deviation, which means some robust statistics with large scattering a data set which is less affected by outliers than variance or standard deviation techniques. In this case, when a real outlier is identified, they are replaced with a predefined local upper-lower bounds. Other tools are, of course, averaging and detrending. Time averaging is related to the assumption that in time bins, the observed phenomenon is stationary. Of course, the extent of this time slot is difficult to quantify and generalized. The problem is about situations where there is an apparent dynamics into the observed phenomenon. In this case, it is necessary to apply the so-called detrending strategies that are used to automatically remove known trends from sub-data. And this is in the picture a quite simple case where there is a constant trend to increase the measured value, and the filtering is applied in order to separate the trend from respect to the actions that are necessary if you want, for instance, to characterize the turbulence metrics. Another important point is the noise that can be generated by the instruments or by the waves, as we already mentioned. Doppler noise is typical when ADCPs are used for measurements. Doppler noise is easily traceable, for instance, from power spectral density maps, because it's basically white noise, typically non-physical, of course, as compared to the -523 law of real turbulent fluctuations in the inertial range. So in some sense, it is easy to recognize, and then it is possible to filter. Of course, there is still a problem related to the fact that the diverging beam technique that Separ was already introduced has the risk to introduce non-physical anisotropy in the measurements. Again, waves, the point here is to isolate velocity fluctuations associated to coherent signals from different positions along the vertical column. In this picture, you can see that from the turbulent kinetic energy spectrum, the Doppler noise contribution is clearly observed as a rather flat distribution at very high frequency. Which is, it seems to be not that relevant, but is fundamental, actually, is a synchronization. And it is important when in complex setups for in situ monitoring of resource and device operation, a large number of time signals are acquired, and typically these data are sent to different acquisition platforms with different sampling rates and time starts. This synchronization is easily obtained using a shared reference signals, typically a trigger signal, and further processing, like for instance, dynamic time warping, can be necessary to filter possible sampling rate inconsistencies. Okay.
Things, I think, because
no, it seems.
Yeah. Close.
Oh, sorry, something wrong is happening. Okay. About data processing, David already mentioned the importance of the format used to convert and make useful data. There are some standards that are coming to the market, let's say. One is about the net CDF format, and there is dedicated software, for instance, one of the partners in the project, who allows conversion from ASCII file to this net CDF format. There are details in this slide for this kind of format, and I would like to spend a few words more later about this topic. But in view of the time, I would like to go as much as possible quick to, maybe I can skip quality control, because David addressed the problem with a very general approach that was, of course, mentioned for waves, but is still valid also for tidal energy characterization. So you will find some more words, and in particular some references as far as uncertainty verification, which is an essential part of the quality assessment and control. Then I would like to move quickly for a few minutes to data presentation and analysis. Again, we make reference, at least with the pictures, with this important project that was held years ago with EMEC, an important partner in the project, because of testing of 2 megawatt scale devices in the fall of Warness, which is one of the sites we have described so far. And this project provided an interesting literature about the characterization of data from in situ monitoring. So we decided to take this as a guideline in order to address a number of aspects. Of course, in data presentation, main issues to be considered: the results characterization for annual energy production, the results characterization for detailed flow analysis, and device performance characterization. So we start from the annual energy production, considering and recalling that raw data consists of a tremendous amount of scattered data that are needed to be organized, because otherwise a huge amount of data will provide basically no information, because too many data means no data, most of the cases. So if we proceed to an extreme synthesis of results data, we can describe the annual distribution in the Tidal site, which is essential for the definition of the annual energy production for a given device. The first kind of presenting data is the Rose diagram, where combined frequency of occurrence and velocity, intensity, and directions are provided in a polar diagram. And you can see here an example. Typically, data are referred to turbine hub depth, and velocity is binned with 0.3, 0.5 meter per second. And as well, the direction of the current is binned in the order of 5 to 10 degrees. Intensity, there are different ways that represent the occurrence of flow velocity or power as input for energy production estimates. Here you can see some examples. We can use exceedance, which means the probability that flow velocity is higher than a given value, or the actual occurrence, which is the probability that the flow velocity is within a given interval or a given bin. In this case, typically the bins are in the order of 0.05 or 0.1 meter per second. Or you get simply the frequency, which is the number of hours per year where the flow velocity matches a given bin value. But if we are interested with some specific, then of course we needed to move to the results of ADCP characterizations, and for instance about the vertical profiling of the flow field. Here you can see classical results in the literature, again from the Readiness project and measurements done by EMEC. And you can see vertical velocity profiles that are binned with different colors according to the flow speed, that are averaged over the full test period that, as we already mentioned, can be in the order of 4 to 5 weeks. Distance from the seabed is, of course, what you find on the y-axis. And measured data, for instance, can be compared with the classical power law. If we want more complex details, for instance, we can consider the effect of flow acceleration, which means to separate data that have been collected during growing or decreasing tide phases. And here we recall the importance of providing metadata. Raw data measurements should be always accompanied by other data that better characterize what was happening in a general sense during the measurement, because then it's very important in order to understand the trends, in order, for instance, to make troubleshooting if some measurement is apparently inconsistent because of some occurrence during the measurement. Another way to present more complex data is, of course, when measurements that are averaged binned from different sensors are compared. And this is, for instance, interesting when you have the possibility to characterize different positions in a given site, or different positions around a deployed device. And this provides, of course, a sensitivity of how much the resources vary in point to point, which of course is important when you deal with, for instance, an array deployment. Again, turbulence intensity, same way to present data with velocity binning and distribution along the vertical column. And of course, after cleaning, to remove, for instance, the Doppler noise. But why not? You can also compare data before and after cleaning to remove the Doppler noise. This was done, for instance, in this post-processing analysis presented in the paper that is mentioned in the reference. And this can be very important in order to understand how much the processing of data has altered the initial raw data that was measured. Again, if we move to much more complex phenomenologies, then we can see, for instance, that we can use more IDCPs, for instance, in this case, 2 4-beam diverging IDCPs, in order to try to measure all the 6 components of the Reynolds stress tensor, and the 3 components of turbulence intensity and length scales. And then, of course, since the quantity of data becomes very important, it is essential to provide a synthesis that, for instance, in this case, there is a reference mentioned here, has been obtained by presenting standard error and mean along a portion of the vertical column, by averaging on a 36 hours data collection by combining ebb and flow data. Same for normal stress and shear stress, as you can see. And finally, of course, as far as turbulent energy spectra, that can be of great importance in order to characterize the risk of fatigue loads on device blades. And not less important, the possibility to calibrate and validate CFD models in order to reproduce the conditions where the devices are operating. There is a very quickly growing literature on computational models that are able to reproduce as much as possible the turbulent flow conditions in a real tidal site. I think we can conclude here this work around the tidal energy characterization from in situ observations. We have discussed about conversion technologies, the scope and objectives of field testing, in particular in situ observations for both results and device. We gave some overview of the methodology and instrumentation used, data processing, and the data presentation and analysis. Thank you very much
Thank you
for a kind attention. I can interrupt the presentation and give the microphone to Marina.
Hi, thank you both. Now we already have a lot of questions. So the first one, I think it was regarding one of the slides from Safer. Why in tidal energy conversion slide, the positioning of the gearbox in both figures is contradictory? One shows it is placed in the front and the other one shows it's in the back. Any specific reason?
Sorry.
We can go maybe back to the slide.
Yeah, I don't know exactly which one it
was.
Maybe this is this one.
Yeah. So I take the photo from the Atlantis. They used exactly the unit of the gearbox and generator together to use exactly the oil for the lubrication in the same cases. So it was just the special cases for the Atlantis, but the configuration is exactly the shaft connected to the generator or directly or by the gearbox. Okay. In these cases, you see it was the two-stage gearbox with the permanent magnet synchronized generator. Inside, that's the Atlantis.
Okay, thank you. So going to the next one. Is Fourier transform an appropriate tool for analyzing scales of turbulent motion, given the non-stationary of turbulent flows? What can be used to capture the large-scale transient motions?
Okay, thank you for this question. Actually, this is a problem that in this period we are addressing, for instance, because we are involved in the development of numerical models to simulate real turbulent flows. And what we find is that, of course, the characterization is, as I tried to describe, is to pass through the autocorrelation of velocity fluctuation, which brings to the definition of power spectra, and actually the evaluation of the PSD of the signal. So moving into the frequency domain is useful. Of course, you must rely on some assumptions about the quasi-stationarity of the experimental signal that you have sampled, and on the ergodicity of the phenomenon. Okay, so based on this assumption, I think that the standard approach is to use this kind of routines. As Adrian mentioned, I would like to point out that, of course, you can develop your post-processing software, but it's better to rely on well-assessed and certified software and routines, because in this kind of post-processing of data, it is very easy to misunderstand, for instance, definitions of quantities, and to, of course, obtain biased data because of numerical errors in the post-processing phase.
Okay, thank you. Moving to the next one. This question is to all, including David. Could you give a budget price for each measuring method to buy, install, and maintain? Something approximate for budget level. Just in the meantime, I'll leave you think if there's any source. We also had a previous course from MaRINET2 on economics. And during that course, we gave a lot of different references for wave, tidal, and offshore wind, where you can find different costs and on different levels as well. So you can check that information first if you want. And if you have any specific values, David or Francesco or Sefer?
I think it's very, again, very dependent on what exactly you're doing and where you are, because they will come up with a cost of the vessel, the type of the vessel you're going to be using. Oceanographic equipment is, generally speaking, fairly expensive. Probably the best is to request the information from the manufacturers. But then the cost starts becoming higher and higher when you look at hiring the boat, getting someone to do it. Best way to do the measurements is to trust it to a supplier who like professional oceanographic companies who do the measurements. But that comes with a cost, of course. So it's very, very dependent on what you're doing. If you're putting one piece of equipment just off the pier, that would probably be one cost. If you're working 500 kilometers offshore with a whole bunch of equipment going in the water and doing different measurements, that will be a completely different story.
Yeah, thank you, David. I would like just to add that this is why we felt important to add some clear message that is very important to compare what you would like to obtain and what is the boundary conditions you are working with, and of course budget, but not only budget, also time is an important variable. Of course, we have our experience mostly on laboratory scale testing. And also in this case, of course, you realize that you cannot measure whatever you would like, or at least the user comes and you would like to measure whatever. Of course, in a real field site, this is quite impossible. So it's important, as you mentioned, David, to exactly define what is the scope, the purpose of your testing, and then to see what is feasible.
Yeah, there are also other costs, like for example, even certifications, as David mentioned before, that are normally not included when you ask for a budget to a specific manufacturer. They normally just tell you the bulk cost of the equipment, but not the certifications or even the costs when it comes to the workload that you will have related to the port and going to the site and everything else. So definitely it's not cheap. We were looking into some buoys last week, and even just the basic buoy was over 100,000 euros. So it's not something that you can say, okay, yeah, it's 10,000 euros for this. No, no way. But it is something important. So if you check between the different references that we have from the previous course, there's also software that WavEC worked, and a lot of projects where both EMEC and CNR worked at. And probably you can also extract information there. In the DTOcean Plus software, for example, you can simulate wave or tidal farms. So you can also, there are some basic, very generic equations, but you can use them as well, especially when you're on the first stages of development and you don't have to be so specific. You can use software, for example, like DTOcean, and it's brand new. So most of the information is, it's very updated. Okay, so I'll move to the next one. What is your view on applicability of the model turbulence spectra, such as the Von-Karman or Keinel, to tidal flow? Would you expect these to apply given different boundary layers and complex channel geometry and bathymetry?
Oh, this is a really good point. And again, as we often mentioned this afternoon, the point is that there are no general conditions, because each tidal site is different from the other one. What I would like to say is that dealing with in situ observation, and then what you can observe, of course, you have some technical limitation that makes impossible to correctly describe what happens in the boundary layer and what happens close to the free surface. In the remaining range, which is typically where you expect the device is deployed, in some sense, you might assume that turbulence is isotropic and homogeneous. So this is what you should consider in terms of the decision of the turbulence spectral assumptions to rely on. But of course, there is nothing well defined. Also because, to be honest, the knowledge about the characterization of tidal site velocity fields is not that wide. For instance, we presented the results for these two literature papers, which represent, of course, state-of-art conclusions based on extensive tidal flow characterizations. There is not much literature on the subject, of course, because there are not much data. And part of them, of course, are also related with the commercial issues, which makes that the data are not that open. So this is a limitation. But again, on this side, I have the numerical developer feeling that there is a very important complementary work that I hope will be focused in the future in order to take as much as possible from real flow characterizations and compare with what a more idealistic condition in a numerical model can reproduce. We are looking forward to what this will be possible in the near future, because there are some promising examples with, for instance, the so-called synthetic eddy models that are very popular in the numerical community. For instance, we are working on a slightly different approach, and it will be interesting to compare with experimental data, of course.
Okay, thank you. And a question, are there existing studies or reports with results about the impacts of biofouling on instruments from that acquisition?
Maybe this is for David, maybe this question.
Sorry?
Yeah, I can jump in. I think, again, it depends on the instruments. You could find separate, quite a few papers covering different instruments. I've seen papers talking about Waveriders and how the marine growth affects high frequency response of those. I can't think from top of my head, but if you Google it, you would find it quite quickly. Datable Waverider biofouling. Similar with ADCPs, manufacturers on their websites would have quite a lot of papers covering that bit as well. Some instruments and different settings would work better, some worse. But I think there is quite a lot out there. It's not one report covering all types of instruments, but manufacturers would have quite a lot of papers covering specific type.
Yeah, I can also think a lot of presentations, especially, well, during the past year with all the webinars that we all had and attended, during courses like this one, or even presentations before even the COVID and everything that are available online, you can find a lot of information there, because even if it's not the complete data, you can see the pictures, which are really astonishing in most cases. And it can give you more idea. In any case, biofouling is also completely related to the location, even the times of the year. In some cases, I've seen studies that they were deploying on exactly the same site, but the difference between deploying on 1 month or the next one was the difference between having tons of mussels in a chain or a mooring, and the next month they deployed another sample and nothing happened. So biology and organisms are very specific to certain conditions, and you also have to take that into account. But yeah, there's a lot of information there.
Yeah.
Okay, next question. Francesco or Sfer, could you expand on how the ADCPs introduce non-physical anisotropy to the data?
Well, okay, using the deviation of the beams, so that's give this the possibility, of course.
You mean the diverging beams?
Yeah. And actually use the other units of the ADCP. It was the multiple sensors units.
Okay, thanks.
You're welcome.
Next question. What flow speeds would you expect at the seabed? And does this have any effect on the stability or the beam angle of the ADCPs that are gravity anchored to the seabed?
This is a good point. I think maybe David could confirm that there are cases that the device is completely lost. Yeah, so yeah, this happens. Of course, maybe it depends that the concrete was not well designed and so on. But this is an important point because, as we mentioned, the test procedures claim that it's better to have sea-based ADCPs. But again, it's very important to monitor possible movements or fluctuations of the position of these devices. So the answer is definitely yes. This is something to be checked continuously.
Yeah, exactly. One of the things that have to be noticed for the data processing is exactly the accelerating and the movement of the structure of these ADCPs. And the best way is exactly mounted in the seabed.
So, David, maybe is that common to use accelerometers on the top of these devices?
Thank you, Francesco. Most of ADCPs, yeah, as you know, they have their tilt and pitch and roll sensors, although majority until recently had only, they didn't have dynamic motion sensors. So they would just have a spot reading of where the ADCP is looking. So you won't take into account the whole motion, the physical motion of the ADCP. Recently, more newer versions started including that high attitude high altitude motion sensors in them, and that's the ones where it started going on to the wave buoys as well, looking downwards, because they can actually take into account the whole motion of the buoy as well. But yes, absolutely, and as you said, Francesco, I've seen so many times the ADCPs either being lost or seabed frames being moved on really highly energetic sites. We had to redesign our frames quite a few times until we got to the point when they're more or less protected from the sides. In addition, if it's a gimbal frame, then the whole the motion of the frame will start affecting the motion of the ADCP as well, and that would change the motion of the beams at the top as well.
Yes, and this is in particular because, of course, as it was apparent from some pictures I showed, the turbulence intensity is relatively much higher on the seabed. So you have acceleration spots that, of course, are prone to generate this kind of movements. Yes.
Okay, thank you. This one is more related to the design. How does the concept of velocity deficit vary for tidal turbines? And how do you decide the spacing of tidal turbines accordingly? I don't know if you have any information on that.
Is that for me?
Yeah.
Okay, sorry, because this is a very general question, of course. Okay, I put these two pictures in our presentation because they are very nicely representing the problem. The problem is that the turbulence intensity has a tremendous impact on the energy mix in the wake of a device, of an extreme device. So if you are in a tidal array, then it's very important to characterize this to understand what is the minimum distance where the next device could be deployed. Of course, for practical reasons, it's better to have a close installation of devices, maybe, for instance, for the substations optimization, the cabling arrangement, and so on. Of course, from the aerodynamic viewpoint, it is completely the opposite. So the spacing is a matter of what happens in the site that you have, and actually this is what comes out from the optimization of the site planning. So for sure, a rule of thumb is that maybe 10 diameters of distance between horizontal axis devices can be a good reference. Different is the case, for instance, with vertical axis devices, because there are evidences that there is a positive interference when devices operate in a close proximity. But this is a completely different phenomenology.
Okay, thank you. We still have two more questions. Why the data measurements taken on more than 5 meters below sea surface? Is it to reduce the effect of waves, or higher speed is always occur at the depth?
Well, as far as maybe Adriana, you can tell. As far as we know, the problem is that, of course, the wave-induced orbital motions determine something that is difficult to separate from the characterization of the real turbulence flow behavior, and also the precision of measurement can be affected. So this is my understanding about this rule of thumb about this upper layer that has to be removed. I don't know, maybe David is more expert on this.
When it comes to ADCPs, if we're using current profilers ADCPs, there is a physical limitation on them, and it has to do with the geometry of the acoustic beams. The problem is there is the main lobe, which actually does the measurements, but there is a side lobe that comes from acoustics, and it reaches the surface before the main lobe can reach. If you sit down, some of the manuals do describe it quite well. So it's actually just sitting down with a pen and pencil and drawing it out, and very quickly it becomes clear. But the rule of thumb is that for ADCPs that have 20 degrees beam separation, you would lose top 6% of the profile and the 6% of the distance from ADCP to the surface. Newer ADCPs have 25 degrees separation, so that's roughly 10% of the profile you would lose from the top. So if it's deployed at 50 meters, you would discard the first 5 meters, the top 5 meters. And it's just geometry of the beams and the side lobe and main lobe of the acoustic signal.
Okay, thank you. Okay, the last question, and then we can move to the wrap-up session. The data between pre and post-processing seem to be quite different. Is that a good proof of good measurement or supposed to be less different?
Okay.
As we present, there is a lot of things that should be noticed at and removed from the data collection. One was the position of the sensors, velocity of the flow, angle of the velocity, white noise, and other things, a lot of things, actually presence of the wave, turbulence, all of the things. I think, yeah, it's depend to recognize all these things. And when you remove the things from all the data, it's, I think it's normally be this difference between the pre and post processing.
Yes. And I would like to add that this is why David put a lot of emphasis of the QA and QC aspects, because since there is so big difference, you need to realize if there is something wrong or it is physical. So.
Yeah, absolutely. And I think it was in your presentation as well, when post-processing, also in the post-processing you look at different phenomena, isn't it? You could be trying to extract one phenomena or the other, and the result might be quite different from the original raw signal if you're, say, extracting only turbulence or looking at only the average currents. Yeah, it might not be that the data is bad, it's just you are singling out something, isn't it? You're interested in. Yeah.
Okay, so we're done with all with the Q&A. Francesco, I leave you for the wrap-up session.
Okay, so I don't have the agenda in front of me. I would like to understand how long we can go.
We had planned to finish around now, 4:15, but don't worry. I mean, I think you can go 15 minutes and the attendees will stay here.
Okay, eventually it can be quicker because, sorry. Okay. Well, basically, we already. Sorry, I don't know where I am. Okay. Okay, recap and finalize. Basically, thanks to the audience and the interesting questions, we already pointed out what for me has happened, David, are the main conclusions of this discussion. Again, as we already mentioned, in situ observations for both wave and tidal means to characterize the environmental factors affecting device operation of a range of spatial and temporal scales of importance to the designers and operators, and to investigate the impacts that this device can determine on the environment. This involves a multidisciplinary approach, and today we discussed mostly aspects related with the results assessment and the device performance and operation. In the second session that will be held in September, more details will be given in terms of the environmental impact. We already mentioned also that in situ operation mills operate in a harsh environment. We already pointed out some tricky conditions and the complex physics to be described. In particular, I would like to stress that there are typically terabytes of data that are processed. So it's necessary a trade-off between clarity and completeness of information for the effective utilization of data. Because as I mentioned, too many data means no data. And extreme reduction means something that could be misleading for the analysis. So data collection is highly sensitive to disturbances, measuring technique limitations, noise. We already noticed that waves in some sense determines problems when the subject is about tidal site characterization. And also resolution issues can be relevant. For instance, for tidal flow measurements related with the too large control volumes with some of the most popular instruments used. This brings to an important point. It is anyhow fundamental to follow accepted test protocols and standard procedures for all the phases of the test program. And this is a subject that brings to a specific area. I think maybe there is not time to go into details, but basically the idea is that we have quality tests that are necessary to give reliable information to developers, investors, certifying and consent bodies. Results should not be dependent on the different metrics conventionally used by data provider. I mean, if tests is done at EMEC or in another field site, the same user would like to determine the same performance for the device. And this means standardization, of course. The approach is then to address issues affecting quality of tests, develop procedures to minimize and quantify errors, and promote wide adoption of procedures and standards. There are many standards that in some sense are related to the activity about wave and tidal energy systems, but only recently there is an effort in order to develop something that is specific for these aspects. The major players involved in this activity is the International Electrical Commission, which has been mentioned several times. The International Towing Tank Conference, so far its activity was mainly dedicated on a laboratory scale modeling, but there is an idea to create a liaison between IC and ITTC, just because the same developer is the first testing a device at laboratory scale, but then the same device, the same developer goes to a field site testing facility. So it's important to have standards that are not completely different if you are at laboratory scale or in a field site. Of course, other important organizations in the sector are the ISO, and for the environmental issues, the International Hydrographic Organizations. There are a number of projects that have addressed the problem, including, of course, the MaRINET project, and organizations like EMEC, who is developing his own standards and proposing standards to the community. At the moment, I think that the most addressed reference is the IEC, and in particular the TC 114 is a working group on marine energy, and this is a list of reports that address specific aspects related to the testing of wave and tidal devices. And as I already mentioned, of course, David can tell us more about this. EMEC is doing a great job in order to develop and propose guidelines for global adoption as the first international standards that are specifically developed for marine energy. In the slides, you will find some more details about some aspects of the characterization of these procedures. Maybe there is no time, of course, to go into details. While I would like to spend a few words on a final aspect, which has been already touched by David, about data exploitation. Data exploitation means to follow what is now referred to as the FAIR principle. FAIR means that data shall be findable, accessible, interoperable, and reusable. This is fundamental in order to give value to all this work that has been done by collecting data from in situ observations. The trend that is trying to be established is to associate a DOI digital object identifier in order to characterize uniquely the data set and to ensure data preservation according to a standard policy. There is a reference about this aspect of data preservation. There is a link. And for instance, EMEC is at the forefront in this respect. They have already access to CNO, which is a publishing organization for dataset with emphasis on marine applications. And so you can access data, as far as they are public, of course, by visiting these websites where data are collected and organized following specific standards. This aspect, I would like to point out, has been dedicated a work package in the framework of the MaRINET2 project. And the idea was to put forward this knowledge about the preservation of data and the accessibility of data to the community. And this is an effort that is being done, for instance, in the framework of CDataNet, which is basically an organization which takes care of the preservation of data and develops approaches for metadata format, definition of quantities, conversion into mapped CDF format, and other services. An example of the involvement of MaRINET2 in this activity can be found, for instance, in the results of a round-robin test for instance, for Tidal devices that has been uploaded by Ephemer in this CNO website. So you can have access to data using this DOI. And again, you find all data organized as I mentioned. Okay, so final takeaways. As we mentioned, successful measurements require a preliminary understanding of underlying phenomena and specific requirements. The choice of wave or current sensors should be driven by scope or site cases. Best practice for waves is the surface voice or acoustic current profilers, while for currents, the same technology called DCP with the sea-based devices is to be preferred. Without quality assurance or quality control, there is no confidence in the measurement results, as we pointed out. Again, monitoring raw data during tests is essential, because when the tests are completed, maybe it's too late for troubleshooting. And finally, data handling practices are extremely important. And just before, we mentioned what is going to be done in order to develop this fair approach to have accessible and interoperable, usable data. The final objectives of what we have discussed today are, if you want to summarize, to foresee device deployment conditions and to inform an effective prototype design. I would like to finish with this example out of our experience in this MaRINET project. There is
Francesco, sorry to interrupt you. We can't see the slides.
Oh, sorry.
It's okay. It's okay.
You can see now?
No, not yet.
Strange. Maybe you were not seeing the slides because
no, we weren't seeing them before, but since you were talking in general, it was okay. But right now, since you said you were going to show an example, I think.
Oh yeah. Sorry.
It's okay.
Maybe now you can see.
Yeah.
Okay, very sorry. I didn't realize I did not share my screen. So okay, it was just to nicely conclude this interesting event. With this example of the long way from initial concept to field site deployment. And this is a real history of a developer, technology developer, who started with a very small device that was tested, of course, in a very small laboratory for a preliminary assessment of the geometry, for instance, of this turbine. Then a larger model was tested in a large fuel tank in order to characterize, for instance, performance, the risk of cavitation on blades, and then finally the assessed design was realized in a larger scale, and the hydrodynamic study was combined with the characterization of a possible PTO to convert mechanical energy into electrical power. And this was the point where the laboratory tests left the way for access to a field site, as it was in the case in Strangford Lough in Northern Ireland. And all this activity was performed as different steps in the framework of the MaRINET project. And so I think it's nice to conclude this event hosted by the MaRINET project and show how much this kind of collaborative activities can be useful in order to support developers for the development of their technologies. So, where we operate, we are not in the middle of the North Atlantic, we are close to Rome, and this is a bird view of our facilities where we work on a laboratory scale. The important point is that, of course, we have world-class facilities that allow to test devices up to TRL4, in some sense 5. And so we are bridging the gap between the laboratory scale and field site testing. And then, of course, we job to David and his colleagues for the final characterization of the Tidal site. Okay, maybe I can stop here. Marina, this slide maybe is for you.
Yeah, well, I would just like to thank you all, both the speakers, David, Francesco, and Sefer. and also the attendees. We had a lot of registrations and a lot of participation today, not only attending the session, but participating in the questions in the Q&A, and also from a lot of countries, not just Europe. So that is also really good. And I just want to remind you that as soon as we upload everything into the project's website, we will send you an email so that you can download the information. We will also send a certificate of attendance, but we will send it when we finish with the second session in September. So if you need any other justification before, just email me to the email from MaRINET that is on the chat and also on the website, and we'll prepare something for you. Then nothing, I don't have anything more. I'll just see you hopefully on September 3rd for the second and last session of the course.
Thank you very
Hope
much.
you enjoyed it.
Thank you.
Thank you.
Thank you so much for arranging everything.
Thank
And
you.
thank you, Francesco. Thank you, Marina.
Thank you for your time.
Bye, David. Bye, Marina, for organizing.
Thank you.
Bye.
Bye.
Have a good weekend. Bye.
Bye.